So in our next section, we're going to talk about what are the different IBGP scaling techniques. Specifically, we're going to focus on route reflection, and then how large-scale route reflection works with route reflector clusters, and then talk about a little bit with confederation. What are the differences between reflection and confederation? When might you choose one over another? And then we'll have separate sections after this where I'm going over implementation examples of both of them. Now, the overall goal or the overall idea of either of these is to eliminate the need for the full mesh. So in the case of route reflection, instead of all routers peering directly with each other, we simply peer to the centralized route reflector, and then the ultimate end result is that they behave similarly to how the OSPF designated router or the ISIS designated intermediate system, the DR or DIS, perform. Now, the end goal of this is that we want to send one update to the route reflector. The route reflector is going to turn around and send it back on to everybody else. But the key point is that it does not modify the attributes when it reflects the routes on. So this means that the end behavior of the reflector is very similar to the DR or the DIS in the terms that the box doesn't necessarily need to be in the data plane. So in other words, you advertise the route to the reflector advertises it to me, but then when I actually route my traffic, I route it directly to you as opposed to using the reflector in the middle. Now, depending on whether that is the case or not depends on the physical design and some other options that we'll talk about a little bit later. But in most practical cases and in most practical service provider designs, the route reflectors will not be in the data path. So they're mainly used as just control plane boxes to host the routing table, and then the actual clients of the reflectors are going to use their internal IGP or maybe MPLS in order to make a decision of how I actually route the traffic. Now, as we talked about, the original idea of doing the full mesh in BGP was not only for having the full view of the topology, but it was also for loop prevention. With the idea being that if I advertise the route to you and you simply don't advertise it onto somebody else, then you shouldn't be causing a loop in the advertisement because they would have to get it directly from me. But in this case, with reflection, now we're breaking that loop prevention rule. So we need something else to introduce in order to add the loop prevention back. And that's specifically what the cluster ID is. So the route reflector is going to drop routes that it receives in with its own cluster ID. Now, specifically, we're going to set this based on we'll see that there's two different fields. There's going to be an originator ID, and there's going to be the cluster ID. Both of these, by default, are going to come from the router ID, but they're two separate fields inside of the actual update. So when we go to send the update on, we'll do a packet capture, and we'll look at the actual format of it and see where these different fields actually fit in, and then how they have an effect on the actual advertisement and the actual loop prevention. But the reflector is mainly adding these two attributes. The other stuff, it's not going to change. So it's adding both the cluster ID and the originator ID based on the client. Now, the route reflector specifically has three different types of peers. We have either eBGP peers, IBGP clients, and IBGP non-clients. Now, the difference between them is that the route reflector processes its updates differently depending on which type of peer the routes came from. So this means that if I am a reflector and if I have an eBGP peer, when I receive an update in from them, I can advertise the route to other eBGP peers. I can advertise it to both clients and non-clients. The same is true if the route comes from an IBGP client. I can advertise it to eBGP peers, other clients, and non-clients. The exception here is when I am a reflector and I receive the route from a non-client. In that case, I'm allowed to reflect it to either eBGP peers or clients, but not to non-clients. And there is a specific reason for this rule, and it has to do with large-scale BGP route reflectors and specifically how you place them in the topology. So in most practical designs, you wouldn't want to have a single route reflector in the network, because then the problem is if that reflector goes down, no one is going to have any routes and they're going to drop all of the traffic. So typically the network is split into what we call different clusters, where in most practical designs, a cluster is going to be based on the physical topology of the network. So let's say we have a network that's made up of the US from West Coast to East Coast, and then like Chicago in the middle. We might have a reflector cluster in Los Angeles. We might have a cluster in Chicago, another cluster in New York, and then do inter-cluster peering between them in order to advertise the routes between the clients. Because ultimately, we don't want to have the whole network rely on just one box's control plane to say whether we're actually going to be able to forward traffic or not. So the clusters are adding redundancy, but they're also adding hierarchy. So specifically what a cluster means is going to be the combination of the reflector and its clients and other reflectors that are using the same client identifier. Now, a good resource for this, just to see it from a high-level overview, is the BGP Design Guide, which is this one here, BGP Case Studies. Okay, if you haven't seen this document before, I would definitely take a look at it, and I'll go ahead and post the link to this here in the chat window. But under this document, under BGP Case Studies, it talks about general things that we've talked about so far, like how does eBGP multi-hop work differently than single-hop eBGP peers. But the other portion that's really good about this document is down here under reflection. How do the reflectors work, and then what would a case with multiple clusters look like? So in this example, they're showing basically a single cluster that is made up of 3 routers. It's made up of the actual reflector, and then it's made up of the clients. Now, when the route comes in from the eBGP peer, it goes to the client. The client is going to advertise it up to the reflector. The reflector advertises it back down, and then we can install the update and use it. So again, the ultimate goal here is that we don't have to do a direct peering between these two because the reflector is advertising the routes on their behalf. Now, this topology is pretty straightforward because there's only 3 routers. Okay, once it starts to become larger, though, it gets a little bit more complicated. So in this type of design, this might reflect that physical topology of the network, where maybe on the left this is Los Angeles, in the middle this is Chicago, and then on the right this is New York. And these peerings here are representing our physical long-haul links in the topology. So we're peering from LA directly to New York. We're peering from LA directly to Chicago, Chicago directly to New York. So now the question becomes, when I receive an update in from the clients and I advertise them to other clusters, do I want the other clusters to reflect them on, or do I want them to have to get from the original route reflector in that cluster? So the ultimate design is variable here. There's no one specific answer to say this is 100% right, the other answers are 100% wrong. It depends on a lot of other factors in the topology. But the main idea here is that this on the left, these 3 routers, these are representing an individual cluster. Now, you would typically have a design that goes a little bit further than this, where you would have multiple reflectors servicing the same cluster. So now in this case, we have a client that is peering with reflector 1 and it's peering with reflector 2. But the idea is that if I advertise a route to reflector 1, I don't want it to have to reflect it to reflector 2 because it should have already got it directly from that client. And from an implementation point of view, this is the specific goal of using the cluster identifier. That the end result is that we still are going to learn the routes, but we're not going to have loops of the updates which eventually need to get discarded. Because when I advertise a route to the reflector, it's going to add the cluster identifier, and if the route gets looped back around and I receive it in with that ID, I have to throw it away. But the issue is that if I have to throw it away, then why would I even want to receive it to begin with? So this is really where we start to get into the peering design and who do we want to be clients of each other. Now, also in practical designs, you'll typically see that reflectors service only one address family. And this avoids what we call fate sharing of our services. So the idea is that if the service provider is doing regular IPv4 unicast routing for the global BGP internet table, but they also have MPLS Layer 3 VPN customers, we don't want someone flapping routes in the internet table to affect the MPLS customers. So in most typical designs, you would have a set of reflectors for VPN v4 for MPLS. You would have a set of reflectors for IPv4 unicast, for IPv6 unicast, just to keep the services out of band from each other, that one of them cannot affect another one. So as I mentioned here, when we're talking about the peerings between the clusters, Whether we actually want them to be clients of each other or whether we want to share the same cluster ID depends on the redundancy design. So the idea is that if we have, if everyone has a unique cluster ID, then we'll get a lot of duplicate routes, which is going to mean more processing, but it doesn't necessarily mean there's a loop in the data plane. So this is a difference than we saw like in redistribution before when we were talking about control plane loops. In those cases, we were talking about infinite loops of the network where the routing table continues to churn and it never makes the correct decision. In this case with BGP, we can have a loop in the control plane which eventually terminates and it doesn't cause a problem. So in other words, I advertise the route to you, you advertise the route to Bob, Bob advertises the route back to me, but since I'm using the cluster ID as part of the update, I know to discard it when it comes back in. The real question becomes that if I am a reflector and you are a reflector and you are appearing with a third reflector, if you and I do not make each other clients and you and the third reflector don't make each other clients either, then we won't reflect each other's routes to other clusters. So the end result should be the same, meaning that everyone learns the routes, but it depends on the redundancy design. Then the issue is that if the peering between you and I go down, I'm not able to indirectly learn your routes through another cluster. So whether this is an issue or not, a lot of times depends on the physical topology. Because if we look at the physical links of the network, maybe there's only one path between New York and Chicago, and that's the same path that is going from New York, Chicago to LA. Well, in that case, it doesn't matter. If the links are in what we call a shared risk link group, then if New York to Chicago goes down, it implicitly means New York to LA is gone. So it wouldn't make any sense for us to make each other clients in that case because there's never a failure situation that having the client relationship is going to help us with. So again, this really depends on the overall physical design of the network. And you would typically see that the route reflectors generally do want to follow the physical topology in peering as opposed to the logical network. Now, we also have a feature that is relatively new that is called virtual route reflectors, where since the route reflector is generally not in the data plane or not in the data path, which again means that you advertise the route to the reflector and the reflector sends it to me, but I'm not going to use them to forward. I'm going to send my packets directly to you. So this means that we don't necessarily have to have dedicated hardware boxes in order to use as the route reflectors. We basically need something that just has a lot of control plane resources. So a more common design nowadays turns out to be use virtual machines for this. So either you could use the iOS XRV, you could use the CSR 1000V, which is in what we are using in this case, or you could use like a Linux box that's just hosting the BGP table. Because the ultimate job of the reflector is just to advertise the routes on. So as long as I have a lot of memory to store the table, as long as I have a large CPU in order to do the best path calculation, I don't need to actually install the routes in the forwarding table because I'm not going to be in the data plane. Now this also goes along with something that is called BGP selective rib download. Now this is used in the case where you have a physical box that you want it to be your route reflector, but you don't actually have enough resources to forward the updates in the data plane or forward the packets in the data plane. And where you see this in a real design is typically for MPLS layer 3 VPN. Because in L3 VPN, depending on how big the service provider is, they may have millions or tens of millions of routes as compared to the regular IPv4 unicast table, which is about 500,000. So the idea of this is that the routing table gets so big that we can't actually install the updates at the line card. But the idea is that if we're not in the data plane, we don't care. So as long as we can install them in the BGP table and then advertise them on, that's all that we care about because we don't actually need to ping the destination. We're not sending traffic there. Now we'll look at some examples of this later. This is the usage of the BGP table map. And if you follow this link, it goes to the document specifically talking about it, which is the selective rib download. It basically means that you're just hosting the BGP table in the control plane, but you don't host it in the data plane. You can't actually forward packets there. You're using it just as a route reflector to advertise the updates on. Now, the other option we'll see that we have is to do BGP confederations. Now, BGP confederations have the same exact goal of route reflection, which is to reduce the IBGP full mesh. The difference between them, though, is that reflection does this by splitting the network into smaller sub-autonomous systems. So instead of having a centralized point that everyone peers with like the route reflector, we break the network into smaller parts, and then we peer based on the physical topology. So in this case, with confederation, the inter-sub-autonomous systems count as an eBGP peering. Or we'll see specifically not a regular eBGP peering, it's a confederation eBGP peering, because there's some specific behavior of the attributes that's a little bit different than regular eBGP. Now, the idea of the confederation is that we can hide the details from devices that are outside the internal network. So you may be peering with level 3, and level 3 is running confederation internally, but you don't need to know those details. You're just using them as transit. You don't care about their internal structure. And the reason why it works this way is that when I advertise an update to my actual eBGP peers, I remove the subautonomous systems from the AS path. So the sub-ASs get stripped. The only thing you then see is my global autonomous system, and you don't know the details of my internal structure. Now, since this is the case, since the sub-AS is removed, you'll see in most cases the confederation uses private autonomous systems, which are going to be the top 1023 addresses, so 64.512 up to 65535. Now, another advantage of using confederation versus route reflection is that you can use different IGPs inside of the different subautonomous systems. So maybe you have multiple networks that are merging together. One of them was using eEdgeRP, one of them was using OSPF. You want to route between them, but you don't want to have to migrate to one protocol end to end. So what you could do is say, well, let's do eBGP confederation on the edge, and then we can just treat each other as separate autonomous systems. But then when we actually go to route traffic out to the global internet, we want to make it look like we're one AS. So we strip the private ASs or the confed AS set from the AS path, and then it looks like we're one internal network overall. Now we'll see that one thing that is very key about the confederations is that there are certain attributes that are not modified when we move between the sub-ASs. And the one that is very important is the next hop value. So normal eBGP peerings will update the next hop value, but a confederation eBGP peering will not. Now, just like route reflection, since we're removing the need for the full mesh, we need to somehow figure out how to now do the loop prevention. So specifically in the case of confederation, we have two new attributes that are going to get advertised with the path. We have the confed sequence and the confed set. Now, both of these attributes never leave the confederation. So they're considered to be non-transitive attributes, which means that when you advertise a route to a true eBGP peer, you don't advertise the confederation set. So similar to like the multi-exit discriminator, I advertise the MED to you, you don't advertise it onto your other eBGP peers because it is a non-transitive attribute. Now we'll see specifically how the loop prevention works is also going to have an implication in the best path selection. Because now we're taking what used to be an internal AS path. So between IBGP neighbors, you normally don't update the AS path. Now we are updating the AS path. And then we have to make the decision, do we want to make it based on the total length of the confed sequence, or do we want to treat it just as one AS overall? Now, when we look at the difference between these, like I mentioned, both route reflection and confederation essentially accomplish the same goal. So why do we need both of them? In reality, the only difference between them is going to be the migration path. Simply because when you configure confederation, it is a disruptive change. You would see that it's very hard to migrate to or impossible to migrate to in certain situations. Where route reflection is easy. You can add reflectors, you can add peerings to them. Once everything is switched over, you can set the local preference higher towards the reflector, start to tear down the old IBGP peers, and then you have a clean path to migrate through it without having to drop the data plane. The confederation, however, you can't do that because we have to stop the BGP process and then restart it with the new subautonomous systems. So if you're thinking about doing one deployment over the other, really the main consideration is, am I doing this implementation from scratch or what we call a greenfield implementation? So if you are building the network from step one, then don't exclude confederation as part of the design considerations. because there are some cases where it is easier to manage versus route reflection, because we're just treating the network like it's a collection of different smaller pieces, as opposed to dealing with the different inter-cluster peerings, or to determine what particular reflectors need to service which clients. But again, you can mix them. So there's nothing to say that you can't do a confederation and then in that confederation do a full mesh of IBGP. Or you do a confederation and then you have route reflectors that are servicing that particular sub-AS. So inside the sub-AS, we do still have the requirement for either IBGP full mesh or route reflection in order to remove that. So again, it always depends on the physical topology and then what does the overall design look like. So as I mentioned, if you want to get some more information on this, there's two resources that I would recommend to look at. This first one here on Google Talks, BGP at 18. This is a presentation by one of the co-designers of BGP. And then the second one is under Cisco Live 365, which is scaling BGP.